So let's look into a very simple setup, okay? A firm is deciding where to source a new product that will be sold in the US, Europe, and China, okay? It's considering options for sourcing the product at either a manufacturing plant that's located at Mexico in Nogales or in Taiwan, China, or a combination of both of them, okay? So the firm expects demand during the first year to be the following. In the United States, the demand is 10,000 units. In Europe, it is 5,000. In China, it's 7,000. Okay. The cost to produce the product is the same, whether it is produced in Nogales or the Taiwan plant. That's just an assumption, just to keep it simple. Now, each individual plant can produce the total expected demand or some portion of the total demand. The product can be shipped from Nogales or Taiwan to the firm's markets according to the following schedule of shipping costs per unit. Okay, so as you can see, if you are shipping from Nogales versus from Taiwan, Nogales is always much cheaper. Between the Nogales and Taiwan to Europe, Taiwan turns out to be cheaper. And of course, Taiwan is very close to China. Some people say it's out of China, some people say don't. I don't want to get into the political discussion. But between Nogales and Taiwan, of course, Taiwan is much more cheaper. And so trying to figure out eventually how do I distribute this movement of products to try and minimize my overall cost. That's basically the question. Okay, should the firm source only from either Nogales or Taiwan or from a combination of both? What's the idea? Okay. So for that setup, let's look into a very simple setup called multiple sourcing. Okay. And this is what we have set up, the same exact story here. Okay, your plants are Nogales and Taiwan. These are the costs of moving one unit from Nogales to US, one unit from Taiwan to US, from Nogales to Europe, from Taiwan to Europe, from Nogales to China, Taiwan to China. Cost per unit, this is dollar per unit. Okay, and these are the demands, overall number of units from each of these locations. United States demands 10,000 units, Europe 5,000, China 7,000. Okay, so the question therefore becomes, how do I distribute what I move from where? And I've already set up my cost buckets. So whatever I put in here as values in terms of units, it will naturally multiply with this or this, okay, and calculate what my overall cost is. So B8 times B3 is basically that cell times this cell. So that gives me my overall cost for that unit and so on and so forth. And this one basically adds up those values. So that's what I'm trying to minimize. So this is a very simple problem. I have no restrictions in place. I have no constraints in place, right? So I am looking at this and I'm saying, between Nogales and Taiwan, Nogales has lower cost per unit for products. So I want to make this entire 10,000 out of Nogales. Okay. In the same way, here I would want to make the entire 5,000 in Taiwan, and I want to make the entire 7,000 out of Taiwan as well, because I'm just going by this guy, and this guy. These are clearly the ones where my cost per unit is lower, and so it's a no-brainer. I don't even have to do any kind of fancy solving. Okay, it's a simple process. The problem with this process is it's too simple, and it's too out of reality, out of rational. The rational is that you are essentially telling yourself that these plants are Hercules plants. They can produce anything and everything for as much as you need. Okay, so irrespective of whatever the cost is, I'll just produce. So Taiwan is capable of producing, 12,000 units or even more if that need was there. Okay, if this demand was higher, I would just produce that much. If this demand was higher, I would produce that much from Nogales. That's not reality. The reality is when I am producing some sort of constraint in the process. So I have some demand constraints here. Okay, the US demands this amount of units. Europe demands this amount of units. China demands this amount of units. And so your overall demand is what? 22,000, right? That's my total demand. What about capacity? Is there a certain constraint on how much Nautilus can produce and how much Taiwan can produce? And if that constraint is not there, you are just opening it up for producing as much as you need, and that's not reality. So we are again going to look into the setting, the simplest setting. Again, from a modeling perspective, always remember lowest hanging fruit, and we will set it up in such a way that our demand is equal to supply. Okay. So with that backdrop, let's look into a basic optimization scenario, because this is important in the context of trying to figure out how to optimize, because now we need to figure out the right context, if you will. And I want you to take good notice of this specific slide, because I'm going to set this up in the same way I had set up your regression analysis strategy. Okay, so optimization problem has 3 parts to it, and any optimization problem has 3 parts to it. And so in part A, okay, you figure out what your objective is. Okay, so as you can see, it's no different than how we looked into statistics. In statistics, you try to figure out what your problem is, right? The same story here. What is your objective? And in this context, your objective is trying to figure out whether you want to minimize something, you want to maximize something, you want to keep something at a fixed value, like the way we did with break-even analysis. What is your objective? That's the first piece of the puzzle. And then what you figure out is, fine, if you want to reach that objective, there are a certain set of variables that you may want to play with to be able to reach your objective. When you are using a software like Solver or any other optimization software, the idea is you don't do everything by yourself. Okay, if you have to do this thing by hand, it's an absolute mess. So how do you manage this thing using Solver or any other software where the software can do the hard work for you? And the work here is in the context of figuring out all those possible combinations of values that could be there, and based off of all of those possible combinations of values for a certain variable that takes multiple possible values, it will choose that specific value for which the objective can be maximized or minimized. And that specific value is figured out much faster by the computer's brain than that of the human brain. Excuse me. So this kind of a variable is also called a decision variable, because it's the decision on the objective that comes from this variable, right? So if I can change variable values, I can then figure out if I want to maximize or minimize my objective and figure out what that exact value is. There is a problem with that though. Okay, so as an example, if I say y equals 3 times x, okay, and x is my decision variable and y is my objective that I'm trying to maximize. Think about it this way. If I ask Excel to solve for this as is, Excel will keep giving me a value of infinity, because it will become what we call greedy. And it's actually the right term to be used, because this kind of algorithm is also called a greedy algorithm, where I have not created a domain for Excel or any other software. I said, go for it. Okay, so it will take as many possible values as it can take. It will find the highest possible value or the lowest possible value to try and minimize or maximize. But that's not reality. The reality is, when we set a certain constraint within x, x can only take a certain set of values, and within those values you have to figure out how your objective can be maximized or minimized. So this is where you hold your horse, your greedy horse, and put check reins to them. okay, so that the HOTS can only look through the check range, nothing outside of it. This is where we set up constraints. So that's step C. In any form of optimization, you'll have these three basic steps: setting up an objective, figuring out what variable you want to change to reach your objective. Even in the goal-seek model, we did the same thing. With data tables, we did the same thing. It was quantity that was the variable that was being altered multiple times to reach our objective. And then what we are saying here is constraints. In the goal-seek approach, in the break-even approach, we had a fixed value, so life was much easier. But the moment we look into one end or the other end of a spectrum, which is the minimize versus maximize, unless we constrain the variable, Excel becomes very, very greedy. And we have to just hold that within a certain set of values that Excel can take for that specific variable, and then play with it to come up with the maximum or the minimum value. So that's the basic idea of optimization. Put that in the context. Let's suppose that these were already known to you, right? So 100 per unit, 225 per unit, and all of those per unit values, the demand values, all of those figures were all known to you. What we have added to the mix is two things. One is, as you can see, this demand adds up to 22,000, but we have also included capacity as constraints in the process. And we are saying that Nautilus can only produce 8,000. Okay, Taiwan can only produce 14,000. And as you can see, it has been dealt in such a way that when you add up the capacity, your demand and your supply are the same, which is 22,000. That's the very basic base case. You want to design your model at the lowest hanging fruit. So that is how an optimization table is designed. So what you're after is trying to figure out the decision variable. The decision variable is how many units should be manufactured by Nautilus for US, for Europe, for China, how many units manufactured by Taiwan for US, for Europe, and for China. So this is where we bring in the context of a variable that takes two suffixes. Okay, so the X sub ij refers to number of units produced in plant I and sent to country J. And so if I say X sub 13, it's number of units produced at plant 1 and sent to country 3. And so as you can see, if I say X sub 11, it basically means plant 1, okay, which is Nautilus, and country 1, which is US. Okay, and that's where those suffixes go. Okay, so X sub 12 basically is the number of units that are going from Nautilus, which is plant 1, to Europe, which is country 2 or location 2. And then X sub 13 is number of units going from Nautilus, plant 1, to 3, country 3, China. Okay, so those are my variables, right? I don't know what they are. This is where I want to optimize the process. All I know is I want to overall reduce my total cost. What would total cost be? I have $100 per unit, and I have X sub 11 units going from Nautilus to US. So total cost from Nautilus to US would be X sub 11 times 100, right? $100 per unit times these number of units. And I do that same thing for all the others, right? And I add them up, and basically all I'm saying is I'm trying to minimize this specific function. This is not your Z test. This is uppercase Z, just a variable. But that's what I'm trying to minimize. That's my objective function. My decision variables I've already identified. And now comes constraints. Because Nautilus and Taiwan has limited production capacity, if I look into it from this angle, if I add these units up, they should be no more than 8,000, right? If I add these units up, they should be no more than 14,000. On the other hand, these two should add up to 10,000. These two should add up to 5,000. these two should add up to 7,000. That's how it is balanced. So those are also my constraints. So from a production capacity perspective, when you add those up, it's less than equal to 8,000, less than equal to 14,000. Ditto for demand, and I'm saying these are equal to 10,000, 5,000, and 7,000 as you go drop down. There is something more. I'm trying to find the total number of units, right? Those are my decision variables. X11, X12, X13, X21, X22, X23. These are my decision variables or number of units. Can number of units be negative? No, because if you don't specify that, Excel can consider whatever value. Excel at the end of the day is part of a machine, and it will only do what the human tells them to do. And so we also have to ensure that these values are 0 or higher, which is what we are trying to define in the context of sign. Okay, so if you want to put this all together, this is what a linear program or an LP means. So this is a very standard optimization approach. It's a linear program. The formulation of our problem is in 3 parts. Okay, you have to minimize this expression where all of these are your decision variables, subject to, ST stands for subject to your set of supply constraints, your set of demand constraints, and of course your sign constraints. You want all of those units to be greater than equal to 0. That's the formulation process. Okay, so when we look into Excel, this is the limited capacity problem here in Excel. Okay, so let's look into the solver output in just a second. All we have created here is something exactly similar, and I want to show you something before we even go into the gaudy details of a solver. Okay, so you have Nogales and Taiwan at all of these different dollars per units, right? The demand is here, the capacity is provided here. What you are trying to provide here is what the right units would be. And I'm going to use solver to solve it, but I wanted to show you that this is such a simple case. You want to also start thinking in your mind and ask yourself, fine, Nogales has a capacity of 8,000. So of these 10,000 units, I shall use the entire capacity of Nogales, right? Because it has much lower cost. And then the remaining ones, I'll use 2,000. And that meets my demand of 10,000. And it also tells me how much capacity has been used here. For Europe and for Nogales and Europe, if you're looking into markets and demands, you have 5,000 units of demand. You already know that Taiwan has a much lower cost of transportation to Europe. And so in essence, you want to use all those 5,000 units from Taiwan. Okay. And then for the final piece, which has 7,000 units of demand, again, you see that Taiwan provides a very small transportation cost compared to Nogales for China. And so as you can see, and this is a balanced equation in this case, I choose 7,000, it's all balanced, and this is how my equation is balanced. Okay, you don't have to do solver for this simple problem, but I want to show you how solver is used. So while using solver, all we do is, and as you can see, these numbers have been also defined previously. So whatever value I plug in here, you multiply that to the dollar per unit to calculate these values. And so eventually you add them up into this one. That's your final total cost. That's the cost you want to minimize. So what I'll do is I'll clean this up and I'll show you what you do in solver. So this is an output of the solver, if you will, okay? And this is exactly in the way that we just discussed. It has 3 parts to it. An objective, a set of decision variables, and a set of constraints. What's my objective? $D$17, which is this cell, D17. That's the one I want to minimize. By changing what? All of these cells, right? And so I just choose those cells and I say by changing those cells because I want Excel to compute that. I'm not giving any value to those cells. But there are constraints in the process. So as you can see, the first three constraints, okay, so the first three ones right here are your demand constraints. So $B, $11 equals $B, $6, which basically is saying that whatever this demand value will be the same as this guy will be the same as this guy will be the same as this guy, okay? And whatever this one adds up to here, whatever capacity I'll use, I'll ensure that this is less than equal to this guy, as you can see here, and this guy is less than equal to this guy, as you can see here. So that is how the demand and the supply constraints are taken care of. Finally, last but not the least is your sign constraint, which is where you again choose all of these cells together, hit greater than equal to 0, ensure that whatever units you are choosing are at least 0 or more. It cannot be negative. And then you can also choose your unconstrained variables non-negative, and you choose a solving method. In this case, it's a simple LP problem. It's a linear programming problem in the same exact setup that we had here. It's a very basic LP formulation. So once we solve this, life is good. You go under data, go to solver, okay, and I'll basically recreate this so that you know what we are doing, okay? So set objective, click on this guy. I am choosing this as my objective, this cell chosen. I don't want to maximize it, I want to minimize it. By changing variable cells, I look at these set of variables, okay? So all of these are the units that Nautilus will deliver and Taiwan will deliver to all of those markets. And so that's the set that I choose. And now I want to start adding my constraints, okay? So my first constraint that I'll add is give me a second here. I have too much stuff here that I don't need. So the first constraint that I'll use is cell F8, and I'll make it less than equal to that cell, okay? The other one that I'll use is cell F9, and it will be less than equal to the 14,000. Sorry, cell F9 less than equal to the 14,000 value. Then what do? I look into this cell B11, and I make it equal to this guy. In the same way, I choose this cell C11, make it equal to this guy, and finally I choose this last cell here, D11, and make it equal to this guy, D6. Okay, so that takes care of my capacity and or supply and demand constraints. Now, last but not the least, I choose all of these cells and I ensure that they're all greater than equal to 0. And I type 0 here, right? So I just type it. And that hits OK. And so now I have all of these constraints chosen in just the right way I want it. Okay, simplex LP problem. So one more time, objective is set to minimize by changing these variables based off of or subject to these constraints. Hit solve, and instantly it solves for it and does exactly the same thing that we just did. Okay, so that's the magic of using a solver. You can keep the solver solution. If you restore original values, I hit cancel so that you can work on this as many times as you need to. Okay. And again, the idea is to work alongside this while you are reviewing my video, to work alongside with this in the Excel. Pause, go back as many times as you want in the video. That's the best part about it, of this virtual environment. And so the final part, the cost modeling part, is something that we will continue to discuss in meeting 3, and I'll set up a different video for that to review for you before we come to our meeting 3. With that, ciao.